Today I would like to discuss torque on a current loop in a uniform magnetic field. So please remember torque, torque equal to force times perpendicular distance. Torque is a force and it's a vector, it's having magnitude and direction. If a current loop, not a straight conducting wire, just a loop is placed in external magnetic field. So if this is external magnetic field, so because of interaction of current with the magnetic field, so this is magnetic field direction and this is current direction, so that causes the loop to rotate. Torque means two equal and opposite forces will be acts at a suspension point that causes to rotate the loop. Yeah, this is the concept of DC motor also. So to this rectangular loop, if you supply electricity, so current is passes through the loop in the presence of magnetic field. So this rectangular loop, we call it as armature. So that will rotate, the concept of electric motor. So let us try to derive expression for torque on a current loop in a uniform magnetic field. Just recall a current carrying conducting wire which is kept in an external magnetic field. It experiences a force. Now the direction of force will be identified by using Fleming's left hand rule. Now this time you can see the magnetic field interacted with current carrying conducting wire. So there is an inward force. So this is inward force direction. If the force direction means, so this is magnetic field direction and this is current direction. You can apply the Fleming's left hand rule. The thumb indicates the direction of force. Suppose if you can reverse the direction of current, what happens? Now this time there is an outward force. The outward force which exerts on that current carrying conducting wire. So in this case there is an outward force. Now this wire is pushing away. So this is the expression for force. How we can write the expression for force? Force F equal to I times L cross B. This is the force which is exerted on an current carrying conducting wire in an external magnetic field. So we can rewrite this as IBL sine theta. Here theta is the angle between magnetic field and elemental length. And when theta equal to 90 degree, the force is maximum. We can write that force F equal to IBL if theta equal to 90 degree. So this is the magnitude of the force which is acting on that straight conducting wire. But our case is we need to apply the same concept to a rectangular loop. Let us try to apply on it. So this is a scenario. A rectangular loop is kept in an uniform magnetic field. So current I is passing through the rectangular loop. Suppose if I divide this rectangular loop in terms of arms, so this is A, B, C, D. If it is A, B and this corner goes to C, and I'll take the bright color. So this corner goes to C and this corner goes to D. Now current is passing through each arm and the direction of magnetic field is uniform. If the interaction of the current with the magnetic field, that causes the loop to rotate. So to rotate, two equal and opposite forces should act on it. So it causes a couple, that we can see, it causes a couple, that couple makes the rectangular armature to rotate. So same situation, a rectangular loop ABCD suspended between bar magnets, and initially there is no current which is applied. So here on small corrections, here animation and make a correction, here it is supposed to be suspended like that. Now when there is no current passes, so it do not rotate anything. So because of the bar magnets or concave magnets, right, situations, so a uniform magnetic field is set up. Suppose current flows in the coil ABCD, that is from A to B, from B to C, and C to D, then D to A. So that is the direction of current. Now the direction of current and the magnetic field, if you can apply Fleming's left hand rule to the arm DA, now force will be act in the plane of the coil in the upward direction. So while applying this, please consider your right hand as a ABCD rectangular coil and use your left hand fingers to identify the direction of force, and place your left hand such a way like that and fold your fingers, and the point finger indicates the direction of magnetic field and the thumb indicates the direction of force and the middle finger indicates the direction of current. So in this case, the net force in the arm DA, the net force which is acting upward direction. Similarly, if you can apply the same, the left hand rule to the downward arm BC. Now in the downward arm B to C, the force which is acting in the downward direction. So in this arm BC, the force is downward direction, force on BC. In the arm DA, the force is on upward direction. So these two forces are equal and opposite. Since they both are equal and opposite, they do not contribute any couple. So they cancel out each other. So force acting on arm DA of the coil is upward direction, and on the arm BC is in the downward direction, which equal in magnitude but with opposite direction to the plane of the coil. So the resultant effect of the coil equal to 0. So that two forces do not contribute to any net force on the coil. Now let's apply it on the arm AB of the coil, now which is exactly the perpendicular to the screen. Now if you can apply Fleming's left hand rule like that, now turn your left hand finger such a way like that, the thumb indicates the direction of force and the point finger indicates the direction of field and the middle finger indicates the direction of current. So now the net force is just coming out of the screen. It is facing just opposite to me. Now in this case, the net force is downward direction. That is the force due to A to B. Similarly, if we can apply the same to the another arm C to D. Now in this case, again the force will be acts. Now this case it will be inside the screen. If you can rotate such a way like that, the thumb goes inside the screen and the direction of current is indicating upward direction and the point finger indicates the direction of magnetic field. So these two forces AB and CD are equal in magnitude and opposite in direction, and they have different line of action. Means the line of action on the plane of the coil. So they produce a torque which starts to rotate the coil in the anti-clockwise direction. Now that causes the loop to rotate in the magnetic field in the anti-clockwise direction. So if the current in the loop is in the anti-clockwise direction, the loop also rotates in the magnetic field anti-clockwise direction. Suppose if we change the direction of current, if we can change the direction of current, the loop will be rotated now in the another way direction. Now let us try to derive the expression for torque. Suppose this is magnetic field which is contributed to a uniform magnetic field. This side is take as north pole and this side is take as south pole. Now in this magnetic field, if we place a rectangular coil, suppose this is a rectangular coil which is placed in the uniform magnetic field. Now this rectangular coil, if I take this as a side, this is P, Q, R, S. Now the PS side is a length of A and PQ side is length of B. Now through this the current is passing. The current let me take as anti-clockwise direction, so it is going along in this direction. Now if I is amount of current, if I equal to current in the coil, current in coil PQRS, and A comma B, these two are the sides of coil. Therefore capital A equal to becomes A times B is equal to area of the coil. Area of the coil. And here very important, we need to think one more is that theta equal to angle between magnetic field B bar and plane of the coil. Plane of the coil. So plane of the coil means, suppose if you consider your right arm as a coil, just punch a vector in your right arm, just stick it like this. Now if you can rotate your arm, so this vector is also rotates. Area is a vector, so the plane having area, so to represent that area we need a vector help. So the angle between magnetic field and the plane of vector, plane of coil, we take that as theta, not the theta of any current element or elemental length. So here the theta factor is very important. So finally we got, now if I write the expression for tau equal to force times perpendicular distance. Now here the force causes the arm PQ, force due to PQ and force due to RS. The force expression we can write at here, the force F equal to, BIL sine theta. So here L equal to elemental length and theta equal to the angle between the elemental length and B. Now this time, so here F equal to, in the place of L I need to substitute, since L equal to B and theta equal to 90 degree. Therefore expression for force, the force F equal to capital B times small b times I. So this is the expression for force. Now if you can substitute that in torque, therefore tau equal to, force equal to capital B times little b times I times perpendicular distance. Now to calculate perpendicular distance, so this is little tricky but easy to calculate. Now we have the armature coil like this. Now when it rotates, so this armature coil will be change its shape, means it makes at an angle. Suppose this is one of the side which we can consider of side of length A, and through the side, if I is current passing through it, so through the sides the current I is passing. Now this side I can take that PQRS, this is a PS side. Now here it is already having a fixed support. On the fixed support it is rotating. Suppose if I take a parallel which is exactly at here, which I need to measure as, if I consider this as theta, now from right triangle POS, I got it at here, one right triangle. So that right triangle here we are measuring. If it is theta, which is P, and perpendicular it is at O, and this is at S, and PS side is A. So from that, can you give the expression for sine theta? Sine theta equal to perpendicular upon hypotenuse. Your hypotenuse value equal to A, means perpendicular upon A. Now we got it, perpendicular distance. Perpendicular distance means that is nothing but P to O. Here we got it, perpendicular distance. Perpendicular equal to A sine theta. So if I take that expression at here, so tau equal to capital B times small b times I times small a sine theta. Now this is going to change as capital B times I times small a and small b times sine theta. Now tau equal to bi times capital A, here in the place of small a and small b I can replace with capital A sine theta. So this is the expression for tau. Tau equal to, therefore tau equal to BIA sine theta. Now here theta is the angle between the area of the plane and B is the magnetic field. Suppose if the coil having capital N number of turns, the coil having capital number of turns, now this tau expression will be changes capital N times BIA sine theta. For a moment, if I write that tau equal to, in the place of NIA, we can write that a term called as little m. I can talk about what it is. So here this expression changes as m times b sine theta. So this I can write in terms of vectors m bar cross b bar. Since tau is a vector, so we need to express in the top in terms of vector notation. Now let's talk about this character. Small m equal to the product of NIA A, amount of current times number of turns and area. So this we term as magnetic moment. Magnetic moment. So this is something we learned in the electricity also, electric dipole moment. So that is P, tau equal to P sin theta. If you remember the same expression for electric dipole moment, so electric dipole moment tau equal to P sin theta. So this is the tau expression for an electric field. But the same expression for the magnetic field tau equal to mb sin theta. Here m equal to nia. Here n equal to number of turns, I equal to amount of current, and a is the area of the loop. Now this is a vector expression for magnetic moment. Suppose what happens when theta equal to 0 degree. When theta equal to 0 degree means the angle between magnetic moment to the magnetic field. So the magnetic moment vector is equal to area vector, area of the loop. Since the magnetic moment formula m equal to nia, here n is number of turns, is a constant, I is not a vector. So here only vector component is only area. So area vector is equal to magnetic moment vector. So if you punch a vector in your right hand palm, so this is the magnetic moment vector. If the angle between M and B, magnetic moment and B equal to 0, then tau equal to 0. It means magnetic moment is parallel to magnetic field vector. So if I show that for a moment, let's observe it here. Here you are able to see a rectangular coil which is kept in the uniform magnetic field. Now if I can rotate, if you can see how the magnetic field is uniformly distributed and the rectangular coil is in the magnetic field. So let me take a good angle so that we can get. Now current in the coil equal to 2 amperes, and here what you are seeing is the red vector. So this is what I am talking about, magnetic moment vector. So this is area vector also, or this we can call as magnetic moment vector. Magnetic moment, we represent that with little m bar. Now at this right situation, the magnetic moment is parallel to magnetic field, so they both are showing in the same direction. Now in this case, the angle between m bar and b bar equal to theta equal to 0 degree. If theta equal to 0 degree, what is the torque? Torque equal to 0. So it do not contribute any torque in this situation. Suppose if I rotate, if I can rotate from 0 to 90 degree, now here you can see, so how the coil is rotating in the magnetic field to an angle of 90 degree. Now where the other two components, so the other two components of the coil is contributing zero net force. So if you divide the armature as a PQRS, so PQ and side is contributes zero force, which they both are equal and opposite. They do not contribute any couple. But the other two, which contributes a net force, here you can see. Now the net force causes here the theta. If I bring back to as original situation, yeah, this is the original situation. Now in this case, In this case, the magnetic moment vector m bar is perpendicular. So the red vector is magnetic moment vector. So the red vector magnetic moment m bar is along in this direction, and magnetic field is perpendicular direction b bar. So b bar is perpendicular to m bar. So here theta equal to how much? 90 degree. So if m bar is perpendicular to b bar, then the torque tau equal to mb. So which is maximum. Tau is maximum. So in a shortcut we can say tau is maximum when m bar, the magnetic moment, is perpendicular to magnetic field vector. So tau is max when m bar is perpendicular to b bar. In this case theta equal to 90 degree, tau max equal to m times b. When it comes to another case, tau equal to 0. Tau equal to 0 when magnetic moment m bar is parallel to magnetic field b bar. So in this case theta equal to 0 degree sin 0, tau minimum value equal to 0. So if we rotate further 0 to 90 and 180 degrees, just the forces will flip each other, but it causes a couple. So finally, the magnetic moment at this moment, the red vector which you are seeing at here, so this magnetic moment is exactly parallel to the magnetic field, which causes 0 torque. But when the coil is rotates at an angle of 90 degree, that magnetic moment is perpendicular to magnetic field vector. It contributes a net torque. Yeah, this is all about a torque on current loop in a uniform magnetic field.